Graph the function f of x equals 2 to the x power. So we want to get a good idea of what the shape of this graph looks like. Let's try a negative number, 0, and a positive number. So f of negative 3 is 2 to the negative third power. Remember, the negative exponent tells us to move that base over a division bar so that it has a positive exponent. And then we can evaluate 2 to the third power. 2 times 2 times 2 is 8. So 1/8. F of 0, if we put 0 in for x, 2 to the 0th power is 1. And finally, f of 3 is 2 to the third power, which is 8. So let's start with negative 3. 1/8 is a very small fraction there, close to 0. 0, 1 is here, and then 3, 8 up here. So we can probably see that if we connect these together, it looks like this. And assume that if you go to the right, then you're raising 2 to higher powers, like 2 to the 4th, 2 to the 5th, 2 to the 6th. And those are going to keep getting higher and higher for y. So yes, that will go up that way. What happens as we go left of this negative 3? So if we have got 2 to the negative 4, or 2 to the negative 5, or 2 to the negative 6, then we have 1 over a number that's getting bigger and bigger. So will this ever be equal to 0? Like 2 to what power would give me 0? Nothing. Because even if you take 2 to the negative 1/1,000,000th power, it's still 1 over 2 to the positive 1/1,000,000th power. It will never be 0. So we're going to go and we're going to kind of approach 0 but not touch it. And so at y equals 0, we have something called an asymptote. And what that means is that we will approach y equals 0, or f of x equals 0, but we'll never actually touch it. That's why we call that an asymptote. So that's the shape of the exponential function, where f of x equals b to the x, and b is greater than 1. Because our base here is 2, that's greater than 1. Our next example, graph g of x equals 1/2 to the x power. So again, we want to look at a negative 0 and a positive and see what happens here. So g of negative 3 is 1/2 to the negative third power. And that negative exponent tells me that I have to flip over a division bar, and then I'll have a positive exponent. So that's really 2 to the third, which is 8. G of 0 is 1/2 to the 0th power, and even if I take that as a quotient to a power, that'll still be 1 over 1, which is 1. Anything raised to the 0th power is 1. And then g of the positive 3, we're going to have 1/2 to the third power. So that's 1 to the third power over 2 to the third power, or 1 over 8. So let's graph that and see what that looks like. Negative 3, 8, 0, 1, and 3, 1/8. So it kind of looks like somebody took our last function and flipped it over a mirror. Because as you go to the left, as this x gets more and more negative, then the function will become a bigger and bigger number. As we go to the right, as x becomes a higher positive number, then this denominator gets larger and larger. And as the denominator gets larger, we get closer and closer to 0. But we don't actually touch 0. This function will never be equal to 0. Never. Because it doesn't matter what the exponent is, you'll never have 0 You'll never have a negative value either, because remember, a negative exponent just moves the base. It doesn't make it a negative number. So all of the outcomes here are in the first and second quadrant again for this exponential function. And this time, the base is a fraction, so the base is between 0 and 1. And that's what this type of exponential function will look like. So notice that every graph of the exponential function will contain these 2 points. And this is the basic exponential function, no shifts. So if you are evaluating a function where x is 1, then you're going to have b to the first power, which is just the base. Whatever the base is, you'll have that outcome for the point. And what if x is 0? If x is 0, then any base raised to the 0th power is 1. So these 2 points will be on every graph, every basic exponential function. No shifts. Shifts are going to change those, of course. So if xy is a point on the graph of an exponential function, what if you have negative x instead? So if y equals a base to the x power, what if you have a negative x? What's going to happen there? You're going to have the reciprocal of y, because that's what that negative exponent does. It reciprocals whatever your value is. So here we have the basic shape of the exponential function f of x equals b to the x, where the base is greater than 0. It's not saying you can't have a negative, but that would be a reflection, right? So the base is greater than 0, not 1. These functions are 1 to 1. That means they are functions. Each x has one y, and each y goes to one x. That's 1 to 1. There's a y-intercept of 0, 1. No matter what your base is, that's a y-intercept for the basic exponential function. There's no x-intercept. Why? Because y never equals 0. It's just not possible. You have an asymptote there. So you have an asymptote at y equals 0 for both of these basic exponential functions. The domain is all real numbers. You can put any real number in for x, and it is a defined point. But the range will only be from 0, not including 0, but from 0 to infinity. And so this is what the shape looks like when your base is greater than 1, when you have a base greater than 1. And it's kind of flipped when you have a base that is a fraction, right? And that's because of that negative exponent rule. So let's graph if f of x equals 2 to the x minus 1 and see what that looks like. You might be able to tell, but let's go ahead and use a negative exponent, a positive exponent, and 0. So if we evaluate the function at negative 2, we have negative 2 minus 1 in the exponent, which is negative 3. So that's 1 over 2 to the third, which is 1/8. If we put 0 in there, then that's 2 to the 0 minus 1, which is 2 to the negative 1, and that's 1 over 2 to the positive 1, or 1/2. And if we evaluate this at 2, then that's 2 to the 2 minus 1, which is 2 to the 1, and that's 2. If we were to evaluate this at 1, let me get one more point here. That'll be 2 to the 1 minus 1, which is 2 to the 0, and that will be 1 for y. So let's plot those points. Negative 2, 1/8, 0, 1/2, 2, 2, and 1, 1. So the points are kind of close together, but we can connect them and know that this is going to keep increasing to the right and decreasing to the left, but never go past that x-axis because y will never be negative or 0. So how does this graph compare to the graph of y equals 2 to the x? How is this different? Well, inside the basic exponential function, So inside where the x is, you have -1. So remember that does the opposite. That moves to the right 1 unit. So you'll notice that every point in this graph is moved or shifted right 1 unit. Every point. And that's why we no longer go through 0, 1. Instead, we go through 1, 1 because of that shift to the right. So these shifts and reflections that we learned in chapter 8 will also apply to exponential functions as long as we know what those basic graphs look like.